Hey everybody, Avery the Applications Astronaut talking to you about extrema on an interval. Now I got another question. What time do astronauts eat? Lunchtime.
First thing we're talking about are extrema. Those would be the extreme values, or the minimum and maximum values of a function on a given interval. So a couple things. First, extrema is the plural form of extremum, which would talk about one minimum or one maximum. So extrema is talking about multiple minimum or maximum values. Also, important to note, when we're talking about minimum or maximum values of a function on a given interval, we're talking about the y values of those corresponding points. So we need to figure out the y values of the function at those given points to determine what the minimum and maximum values are. That brings us to the second vocabulary term, an absolute minimum. That would be the minimum value of a function on a given interval. This is also known as the global minimum. So this is the lowest y value of a function on a given interval. Whereas the absolute maximum is the maximum value of a function on a given interval. It's the greatest y value of the function on that given interval. It's also called the global maximum. A relative minimum would be the lowest point on the graph on a particular portion of the interval. So the lowest y value of the function on a particular portion of the interval. It's also called a local minimum. So local min and relative min mean the same thing. A relative maximum would be the highest point on the graph on a particular portion of the interval. So the highest y value for the function on a particular portion of the interval. It's also called a local maximum. So if we look at this example down here, you can see some examples of relative mins and relative maxes. Now note the lowest point or the lowest y value that the function reaches, that is going to be your absolute minimum. The highest point or the highest y value that your function reaches, that's your absolute maximum. But relative mins and maxes are just the highest or lowest y values on certain intervals or portions of the graph. Now, this is an important note down here. Extrema can occur at interior or endpoints of an interval. Endpoints always creates a relative extreme value. So if you are trying to determine the relative mins and maxes of a function on a given closed interval, meaning that the endpoints are included on that interval, then you know each of the endpoints is either going to be a relative min or max. It could be an absolute max, like it is here, where it's the highest y value on that given interval, but it's definitely going to be a relative min or max. So you have to know that if you're looking for relative extrema on a closed interval, meaning the endpoints are included, your endpoints must be relative mins or maxes. You have to determine which, and we'll get into that later on. Now, a critical number says let f be defined at c if f prime of c is equal to 0, or f is not differentiable at c, then c is a critical number of f. So all this is saying is that a critical number is just an x value at which the derivative of your function equals 0 or is undefined or does not exist. So if the derivative of your function equals 0 at a particular x value, that x value is a critical number. If the derivative of your function does not exist at a particular x value, that x value is a critical number. Now, these critical numbers are important because they're x values at which your function will likely have a relative max or a relative min. Note, when the derivative does not exist, you will only get a relative max or min if, at that particular x value c, you have a cusp or a corner. A vertical tangent will not give you a relative max or min. A discontinuity will not always give you a relative max or min. Here, when the derivative of your function is equal to 0, you will likely get a relative max, like we see here, or if it were facing the other way, a relative min. Now let's talk about the formal definition of extrema. So this says let f be defined on an interval I containing c. 1. F of c is the minimum of f on I when f of c is less than or equal to f of x for all x in I. Now this makes sense because f of c, this y value, is going to be a minimum of your function f on a interval I when that y value is less than or equal to every other y value on that given interval. Same thing with a maximum. F of c is the maximum of f on I when f of c is greater than or equal to f of x for all x in I. So when f of c, this y value, is greater than or equal to all other y values for this given function on a given interval, then it is going to be a maximum value. Now, the extreme value theorem says if f is continuous on a closed interval ab, then f has both a minimum and maximum on the interval. So all this is saying is that if you have a function on a closed interval, AB, meaning that the endpoints are included in your interval, then your function has to have a min and a max value on that given interval. And be aware, because it's a closed interval, meaning that your endpoints are included, your endpoints could be both your min and max values. They could be one of your min or max values. They could be neither of your min or max values. So just be on the lookout for your endpoints. They could be your minimum or maximum values because it's a closed interval. Now let's talk about relative extrema at critical numbers or endpoints. So this says if f has a relative minimum or relative maximum at x is equal to c, then c is a critical number of f or the x value of an endpoint on the given interval. So all this is saying is that if your function has a relative minimum or a relative maximum at a particular x value, c, that x value must be a critical number, meaning that the derivative of your function at that given x value is equal to 0 or it does not exist. Or at that particular x value, your function has an endpoint. So like over here, we have a relative min at our leftmost endpoint and we have a relative max at our rightmost endpoint. So all you need to know is that relative extrema, relative min and max values of a function can only occur when that x value is either a critical number or an endpoint. Now let's talk about finding extrema on an open or closed interval. So to find the extrema of a continuous function f on the open interval ab or the closed interval ab, the first thing you're going to do is find the critical numbers of f on the open interval. So we need to figure out at what x values does this function have a derivative that equals 0 or does not exist. From there, we can evaluate the function f. We can take those critical numbers, plug them into the function f, and see what their y values are. Then, if f is on a closed interval, if your function is on a closed interval, we also have to evaluate the function at each of the endpoints, at x is equal to a and x is equal to b, because we said earlier that there's definitely going to be a relative min or max at each of the endpoints, but we have to determine if it's the absolute min or absolute max. Lastly, we look at all the y values that we got from our critical numbers and from our endpoints. The least of the y values is going to be your minimum. The greatest of the y values is going to be your maximum, and you're done.
Time to straighten up and fly right. It's example time.
Now example 1 says find the value of the derivative, if it exists, at each relative extremum. So here we have a function and we have a point at which the function has a relative max or min. It should make you think real quick, well, if I'm finding the derivative at a relative max on a given interval and it's not an endpoint, then the derivative should either equal 0 or not exist, because we said critical numbers are x values at which the function has a relative max or min. So if 3 is the critical number of this given function, then the derivative of this function at x is equal to 3 should either equal 0 or not exist. So let's find out. Here, we're going to take the derivative of this function and then evaluate it at this given point. To take the derivative, it looks like it would be a quotient rule problem. But this is one of those tricky ones where we could actually simplify it and not use the quotient rule, and it'd be way easier. What I can do is distribute that 9 in the numerator. I can then take this x cubed and put it under each term in the numerator. I can then simplify this. The x squared cancels out with this x to the third in the denominator, just leaving one x down here, and this stays 27 over x cubed. Now I can take the derivative of each term separately, and instead of writing it like this, what I'm going to do is take this and make it 9 times x to the negative first power, and make this 27 times x to the negative third power. Now you see, all I have to do to take the derivative here is bring this 9 out front by the constant multiple rule and use the power rule here. So this would be negative 1 x to the negative second power. Over here, take the 27, move it out front, and use the power rule here. This would be negative 3 x to the negative fourth after I take the derivative. Now I simplify this, and I can rewrite it with positive exponents by bringing these back down to the denominator. If I wanted to, I could put this back into one fraction by giving these two fractions a common denominator. I would just multiply this one by x squared over x squared, and then now they have a common denominator, so I can combine the numerators. And if I wanted to just make it look a little nicer, I could factor out a 9 in the numerator. Boom, got my derivative. Now, I want to find the value of the derivative at my relative extremum. So here, my relative maximum is 3, 2. So to evaluate the derivative at this given point, I'm going to take the x value here, my critical number, and plug it in for x down here in my derivative. So when I plug in 3 and evaluate this, 3 squared is 9, times -1 makes it -9, plus 9 makes it 0, times 9 gives you 0 over 81, which is 0. And that makes sense because if we're having a relative maximum value at this given point, then your derivative of your function at this given point should either equal 0 or not exist because it's a critical number.
How'd the rocket lose its job? It was fired. You try.
Okay, we're doing the same thing. We're evaluating the derivative of this function at its relative maximum, pi over 2, 1. And we said, because we already know this is a relative maximum, the derivative of this function at this given point should either equal 0 or not exist. Based on this graph, it looks like the derivative should equal 0. So let's make sure that's the case. We'll take the derivative of sine, which we know is cosine. Wow, that was easy. So all we have to do now then is evaluate the derivative at this given point, which we know is where the relative maximum occurs. So we're going to take pi over 2, plug it in for x, and when we simplify cosine of pi over 2, we get 0. And that makes sense, right? The derivative of our function at pi over 2 is equal to 0 because the derivative of your function at a given critical number must either equal 0 or not exist. And here you clearly see that it has a horizontal tangent line, meaning that the slope of your tangent line is 0, meaning that a relative extreme value is going to occur at this given point. Now, example 2 says find the value of the derivative if it exists at each relative extremum. So we're doing the same thing. So this time we have a function f of x is equal to the absolute value of x minus 1. And we see the graph over here. And we know that at 1, 0, this graph is going to have a sharp turn. It's going to have a corner, meaning that at this particular point, the derivative does not exist. So what should happen here is we should take the derivative of this function, and when we plug in this value, it should not exist. So let's check to make sure that's correct. When you're taking the derivative of an absolute value function, you need to break it into a piecewise function. And now in order to break this into a piecewise function, what you're going to do is you're going to say when x is greater than or equal to 1, the absolute value doesn't matter. If I plug in 1 or 2 or 3 or 4, the absolute value does not affect what happens in here because it's going to be a positive number. So when x is greater than or equal to 1, we just have x minus 1 for this function. But when x is less than 1, the absolute value comes into play. So if I plug in -1, -1 minus 1 is -2, and then the absolute value of that makes it positive 2. So I write this as the opposite of whatever x minus 1 is when x is less than 1. So now I have broken this absolute value function into a piecewise function. So now I can find the derivative. Now, how do I find the derivative of a piecewise function? Well, remember, in order for the function to be differentiable at whatever x value the piecewise function breaks up at, so at x is equal to 1, we need the derivative as x approaches 1 from the left to equal the derivative as x approaches 1 from the right. So let's take the derivative of each part of this piecewise function and see if it's the same number. If it is, then it's differentiable and the derivative is whatever we get. If they're different numbers, then it's going to be a corner. So let's find out. If I take the derivative of the first part of the piecewise function as x approaches 1 from the right, x value is greater than 1. Derivative here, I just take the derivative of each term. Derivative of x is 1, derivative of 1 is 0. So we get 1 minus 0, which is 1. The derivative of the second part of the piecewise function, the -1 just pops out front, and I take the derivative in here of x minus 1, which we said was 1, multiply that to the -1 that was out front, and we get -1. So the derivative as x approaches 1 from the left is equal to -1. The derivative as x approaches 1 from the right is +1. These are two different numbers. Because we have two different slopes coming in from the left and the right, we know that the function must have a corner at x is equal to 1. Therefore, the derivative at this particular point does not exist. So f prime of 1 does not exist. And again, this makes sense because this function has a relative max at this point. Therefore, 1 had to be a critical number, meaning that the derivative of the function at that particular critical number had to either equal 0 or not exist. And it does not exist.
I could probably beat up Captain Kirk, but not Spock. You try.
Okay, doing the same thing here, we have a function and we have a relative minimum of that function at -1, 0. So we know that x is equal to -1. That is a critical number, meaning that the derivative of this function has to either equal 0 or not exist at this particular x value. So let's make sure that's the case. Here, you see we have x plus 1 raised to the 2/3 power. Remember, anytime we have something like this being raised to the 2/3 power, we have an even over odd fraction that is less than 1. We know that's going to create a cusp. And where's that cusp going to be? It's going to be at whatever x value causes this in here to equal 0. So that would be at x is equal to -1. Yep, that's where our minimum occurs. So we see in our graph, we do have a cusp at x is equal to -1. So we need to show then in our derivative that the derivative of this function does not exist because it's a cusp. So let's do this. To take the derivative of this function, I have to use the chain rule. I'm going to take the derivative of this outer function, which uses the power rule. So it's going to be 2/3 x plus 1 to the 2/3 minus 1 power, so that would be the -1/3 power. And then we multiply that by the derivative of what's in here, which would be 1 plus 0. Oh, so that's just multiplying by 1, so that doesn't really do anything. So we can just write it as 2/3 times x plus 1 to the -1/3 power. We can then rewrite this with a positive exponent by bringing it to the denominator, and now we have our derivative of our given function up here. Now we need to evaluate this derivative at this given point. So we're going to take this -1, plug it into this derivative down here for x, and when we simplify, we end up getting 2/0, which is undefined. Now because it's undefined, we have to say that the derivative of this function at this particular point does not exist. And again, that makes sense because this is a cusp, and the derivative at a cusp does not exist. Now example 3 says find the critical numbers of the function. So here we have our function f of x is equal to x to the 4th minus x squared. So remember, critical numbers of your function occur wherever the derivative does not exist or wherever the derivative is equal to 0. So either way, we got to find the derivative. So let's take the derivative of this function. To do that, we take the derivative of each term separately. The derivative of x to the 4th is just going to be 4x to the 3rd power. The derivative of -8x squared, the -8 just stays out front by the constant multiple rule, and we just take the derivative of x squared, which becomes 2x to the 1st power. We can then multiply that 2 to the -8, and we get -16x. So we have our derivative. Now again, critical numbers occur wherever the derivative is equal to 0 or wherever it does not exist. So is there anywhere where this function right here would not exist? No, this is just a normal cubic function. So we need to check where this derivative then would equal 0, because that is where the critical numbers are going to occur. So we set this equal to 0, and we solve for x. So how do we solve this for x? Well, I know I could factor out a 4x from each of these, and then in here we now have x squared minus 4, a difference of squares, which factors into x plus 2 times x minus 2. We then have 3 different things multiplied together that equal 0. So by the zero product property, we can set each of those things equal to 0 and solve for x. So over here, to solve this for x, we divide both sides by 4, we get x is equal to 0. Over here, we add 2 to both sides, we get x is equal to 2. Subtract 2 from both sides here, and we get x is equal to -2. So our 3 critical numbers for this particular function right here would be x is equal to 0, 2, and -2. And you can confirm that with the graphing calculator. You see that at x is equal to -2, we have a relative min. At x is equal to 0, we have a relative max. At x is equal to 2, we have a relative min. At each of those points, the slope of the tangent line to the curve is equal to 0.
How do you know if the moon has had enough to eat? When it's full. You try.
So we're doing the same thing here, except this time we got a trig function 2 secant theta plus tan theta. Now notice that we're only on this given interval from 0 to 2 pi. So to find our critical numbers, we need to figure out where the derivative of this function either does not exist or is equal to 0. So first thing we need to do is take the derivative. So let's take the derivative of this function. To take the derivative of this function, we take the derivative of each term separately. The derivative of 2 secant theta, the 2 just pops out front by the constant multiple rule, and the derivative of secant theta is secant theta tan theta. Then we take the derivative of tan theta, which is just secant squared theta. Now, because the whole goal is to figure out where the derivative does not exist or equals 0, we need to try to simplify this as much as possible. So we can factor out a secant theta from each of these, and then tan theta is technically sine of theta over cosine theta, and secant theta is technically 1 over cosine of theta. Now, why do I do that? Because you can see in each of these terms, we have a 1 over cosine of theta, which is secant theta. So I can factor out another secant theta. When I factor out secant theta from here, this just becomes 1. When I factor out secant theta from here, that would be 1 over cosine. We're just left with a sine theta times 2, so 2 sine theta. This is our derivative of our given function up here. Now note, because our original function has a secant theta, which is 1 over cosine theta, and a tan theta, which is sine of theta over cosine theta, we can't have any values of theta that cause cosine to equal 0, because that would cause the denominators up here to equal 0 and be undefined. So we have to set a restriction where theta cannot equal pi over 2 or 3 pi over 2, because at those two values of theta on this given interval, our original function would not exist. It would have an asymptote. So we have to say that theta cannot equal these two values for this given derivative either. Now, we need to figure out where this derivative is equal to 0 or does not exist, because at those values, we will have critical numbers. So let's first find where this derivative equals 0. So we're going to set the derivative equal to 0 and solve for theta. So because this times this is equal to 0, we can technically set each of those equal to 0 separately and solve for theta by the zero product property. So here, if I want to solve this for theta, what I'm going to do is square root both sides. That way I just get 0 is equal to secant theta. Now, secant theta is just the same thing as 1 over cosine of theta. So how would I solve this? Well, let's just look. What value of theta could you plug in here that would make this whole thing equal to 0? Nothing, right? Because if you cause this down here to equal 0, this would be 1 over 0, which is undefined. That's not equal to 0. So there's no value of theta over here that would cause this to equal 0. What about over here? Well, let's solve for theta. So let's subtract 1 on both sides, divide both sides by 2, and then we think, is there any value of theta that would cause sine to equal -1/2? In other words, what is the inverse sine of -1/2? Well, that would be 7 pi over 6 and 11 pi over 6 on this given interval. Both of those values of theta would cause sine to equal -1/2. So what we can say is, at each of these values of theta, we have a critical number for this given function. And we can confirm that with our graph. We see that at each of these values, our function has a relative max and a relative min, meaning that the slopes of the tangent line to the curve at those particular x values, those particular critical numbers, are equal to 0. Now, the last thing I want you to note is that we didn't choose any of the values of theta that caused this to be undefined because they were restricted at the beginning of the problem, because at those particular values of theta, there were asymptotes, and you can't have a min or max value at an asymptote. Now, example 4 says find the extrema of each function on the given interval. So we have our function and we have our interval. And we want to find the extrema, which means we want to find the min and max values of this function on this given interval. So to find min and max values, we need to figure out at what x value do min and max values occur. Well, those would be at critical numbers. So we need to find the critical numbers, and then from there we can take those critical numbers, plug them back into the function, and get the y values that go with them. And don't forget, this is on a closed interval, meaning there are brackets here, meaning that we have to test our endpoints as well. So we're going to take these x values here, plug them into the function, and get the y values that go with them. We then examine the y values of the critical numbers and the y values of our endpoints and determine which one is going to be our maximum y value and which one is going to be our minimum y value, and that would be our answer. So let's do this. First thing we need to do is take the derivative of our function in order to figure out what the critical numbers are going to be. So we take the derivative of our function here, and in order to take the derivative, we take the derivative of each term separately. The derivative of this first term, we use the constant multiple rule. We take this 3, move it out front, and then we use the power rule with x to the 4th. So it becomes 3 times 4x to the 3rd power. Then we take the derivative of this term. The 4 stays out front, and we just take the derivative of x cubed. So with the power rule, we get 3x squared. Then we multiply. -4 times 3 gives you -12. 3 times 4 gives you +12. So we have our derivative. Now remember, the critical numbers occur wherever the derivative of your function is equal to 0 or wherever it does not exist. Is there anywhere where this function right here would not exist? No. So what we can do then is we can just set it equal to 0 and solve for x. So let's do that. How do I solve this for x? Well, I can factor out a 12x squared from each term. And now again, I can use the zero product property. Since this times this equals 0, I can set each of these separately equal to 0 and solve for x. So how do I do that? Well, in this first part, I divide both sides by 12 and then square root both sides. I get x is equal to 0. Over here, I add 1 to both sides. I get x is equal to 1. So our two critical numbers for this given function right here would be x is equal to 1 and 0. I'm going to then take those critical numbers, plug them back into the original function, and get the y values that go with them. So let's plug in 0 to the original function. I simplify, and I get a y value of 0. Let's plug in 1. If I take 1 and plug it into the original function, I simplify and I end up getting a y value of -1. So these are my two y values for my critical numbers. But again, because it's a closed interval, I have to test my endpoints as well. So I'm going to take -1, plug it in the function for x, and simplify. And when I do, I end up getting 7. I'm going to take 2, plug it in the function for x, and simplify. And I end up getting 16. Now, I look at all of these y values, and I determine which one is going to be my minimum and which one is going to be my maximum. So my minimum is my smallest y value. So what is the least y value here? That would be this -1. That's going to be my minimum. So I'm going to have a minimum of -1 at x is equal to 1. My maximum would be the greatest y value. So that would be here. So that would be 16. So I'm going to have a maximum of 16 at x is equal to 2.
What's the best way to organize a space party? You're going to have to plan it. You try.
Doing the same thing, we want to find the extrema of this particular function, and now they don't give us an interval. Well, the reason for that is because this function has an interval embedded into it. Do we know what this function looks like if we were to graph it? Yeah, it's a semicircle with a radius of, if I take the square root of this, 2, so it looks something like this. So we know that this function only exists from -2 to +2. So that's going to be our interval for this function, and we include those endpoints because we can plug in -2 and 2 and get 0 here. But anything greater than 2 or less than -2, we get a negative number under our radical. That's why it's not included on this given interval. Now, in order to find the extrema of this particular function, we need to find the critical numbers. And the critical numbers are going to occur at whatever values of x cause the derivative of this function to equal 0 or not exist. So we clearly need to find the derivative of this function. So how do we find the derivative of this function? Well, we rewrite this. Instead of having a radical, we're going to rewrite it with a rational exponent. So we're going to put it to the 1/2 power. And now the derivative of this clearly requires the chain rule. We have to take the derivative of our outer function, which would be 1/2 4 minus x squared to the -1/2 power using the power rule, and then multiply it by the derivative of our inner function. And the derivative of this inner function is going to be 0, and then over here, -2x to the first power. Okay, so this is just going to become -2x. Here, I can rewrite this with a positive exponent by bringing it down to the denominator with the 2. This, again, became -2x, so I can multiply this. This is the same thing as -2x over 1, so I just multiply the -2x to the numerator. The 2's then cancel each other out, and I'm left with -x over rad 4 minus x squared, because we just changed the 1/2 exponent back to a radical. Now, we need to figure out, where does this derivative either equal 0 or not exist? Well, where does it not exist? Well, it wouldn't exist at whatever x value causes this denominator to equal 0. So that would be 2 and -2. But those are already our endpoints. And we learned from last time, anytime we have a closed interval like this, we're automatically going to check our endpoints for extrema. So we don't have to write that because we're already going to check those anyway. What about the values of x that would cause this to equal 0? Well, that's whatever values of x cause the numerator to equal 0. So what values of x would cause this to equal 0? That would be 0. Now, to determine our extrema, our min and max values, we need to take our critical number and our endpoints and plug them into our original function to get the y values that go with them, and then we'll judge the y values. So let's start with our critical number here, 0. We're going to take that, plug it into the original function, get the y value that goes with that, which is 2. Then we take each of our endpoints and plug them into the original function. If I take -2, plug it in the original function, I end up getting 0. If I take +2 and plug it in the original function, I get 0. So now we examine the y values that we got for our critical number and for our endpoints and see which of these would be our least y value, which is the lowest y value. That would be our minimum. So that would be these zeros here, right? So the minimum of our function is 0 at x is equal to -2 and x is equal to +2. We then know the maximum then would be 2 for our function at x is equal to 0. So those would be our min and max values.